So we're going to find the radius of convergence of this power series. And the first thing we do is apply our ratio test. We take the limit as n goes to infinity of a sub n plus 1, which is x to the n plus 1 over n plus 1 factorial plus 1 times basically the reciprocal of this, which is n factorial plus 1 over x to the n. And then we simplify, take our limit, and see what we have. So we have the limit as n goes to infinity. We're going to see what all canceling we can do, and there's not going to be a ton. But first off, we can rewrite that as x to the n times x. These normally we expand them, but because of the plus ones, we're not going to be able to do any canceling, but that's okay. We have n factorial plus 1, and this is over n plus 1 factorial, and this is over x to the n. So we can see that the x to the n's cancel, which are going to allow us to pull the x out of the limit because it no longer depends on n. So we have the limit as n goes to infinity, and now we no longer need to write the absolute values because these will always be positive. Oh, lost my plus 1 there, excuse me. So the question is, where does this limit tend to? And again, we can't really do any canceling because of the plus 1s, but that's okay. Now, as n goes to infinity, these plus 1s essentially don't make a difference. And so what we end up with is n factorial over n plus 1 factorial. So this is an nth degree polynomial over an n plus first degree polynomial. And what we know from our study of rational functions is that numerator is going to be much larger than the denominator, which is going to pull this thing down to 0. So that means this thing is basically 0, which is always going to be less than 1. That means our radius of convergence is infinite. So this power series converges for all values of n.